Today on How It's Made. Photographs, putting you in the picture. Fur tanning, hair care secrets revealed. Welding electrodes. You'll want to join us for this one. And electric violins. Making these is a fiddly operation. But first... In the 1830s, the first photographers used light-sensitive chemicals to capture images on paper. Today, machines do much the same, but with amazing speed, accuracy and versatility. In this digital age, there are still many who stick to this tried and tested method. The photo lab receives envelopes containing rolls of film for developing. Processing will turn each exposure into a negative image, then a positive one. That positive is what we know as a photograph. A scanner takes a digital photo of the order details specified on the packages. It tracks things such as the print size and finish, and the number of copies that have been ordered. A conveyor then sorts the envelopes into bins, grouping them with similar orders. Next, a machine extracts the film rolls from the metal capsules in total darkness. Exposing the film to light would ruin the photos. The envelopes go into bundles so they can be later reunited with the right pictures and negatives. Here's what the machine looks like on the inside. A blade cuts open the metal capsules and another slices off the leader. The machine unravels and lines up as many as 60-meter-long films end to end. A sticker joins the ends and identifies each film with a barcode. The machine measures the assembled strip, then winds it onto a reel inside a metal box. Another machine unwinds the reel and runs it under an infrared light so that a technician can check it for tears. Just one tiny tear could jam the machine and ruin all the photos. If a tear is found, it's repaired by hand. The technician makes the repair in total darkness. First, he applies tape to reattach the area. Blades then cut the tape evenly on both sides. The technician is able to see what he's doing on a TV monitor hooked up to an infrared camera inside. Developing the exposures requires 4 chemical baths, still in complete darkness. In the first, sulfates make the image appear as a negative. The second includes acetic acid to halt the effect of the sulfates. The last 2 baths preserve the image and rinse away chemical traces. To print the pictures, the negatives are loaded into yet another machine. This one contains light-sensitive paper. All it takes is a flash to transfer the image. A sensor instantly adjusts the intensity to correct any improper exposure by the photographer. To develop the prints, the paper goes through 4 chemical baths, similar to those used for the negatives. One bath reveals the image. Another stops that process, and 2 more preserve the image and rinse off the chemicals. This time, however, the paper then heads into an oven to dry for 2 minutes at 70 degrees Celsius. Now, a technician marks the pictures that are too bright, too dim or out of focus and removes them for redeveloping. Next, a machine unwinds the strip, scans the barcodes and cuts out the pictures that belong together. It also cuts the negatives into numbered strips of 4. The photos and negatives are slipped into an envelope. The computer shows just what to include, and a machine provides the film's original package. When you get your photos, you can check them against your original order, so you can make sure that everything's picture perfect. Fur was first worn to keep people warm, before for some it became a fashion accessory. Tanning is the process which turns a pelt into leather. Today the process is much as it has always been, and the furs still provide old-fashioned warmth. These beaver pelts have been purchased at auction. They're sorted and the quality of the hair is inspected to determine the type of garment they're suitable for. A lot number is hammered into the underside of the pelt. It perforates the skin. This technique is used so that the number stays on the pelt during processing. The ear cartilage is cut out using a pneumatic punch. It's important to get rid of the cartilage early on to enable the pelts to pass through machines during the tanning process. The pelts are slightly dry because of preservation techniques used before they were delivered to the tanning plant. So they're put through various chemical washes to rehydrate them. The final bath contains tanning chemicals which convert the underside of the animal skins to leather. The supple leather texture will eventually allow the pelts to be shaped into garments. Between each wash, the furs go into a wringer. It spins out the excess liquid. All that moisture has caused the pelt to thicken, so they thin it down with a spinning blade called a flesher's knife. You need to be an expert to wield this tool. One false move and you'll cut into those follicles and lose fur. Next, sawdust is shoveled into a large drum. The pelts are placed in the drum along with the sawdust and a mineral solution is added. The drums turn, tossing it all for about half an hour. This cleans and conditions the leather side of the pelts. The furs are still damp when they emerge, so they are hung over wooden dowels to dry, leather side up. The rest of the sawdust will fall away in subsequent operations. Now the pelt's long hair is scraped off to expose the downy undercoat. This undercoat has a more desirable look and texture. A generous amount of oil is rubbed into the leather to lubricate it. Then the pelt is tossed into a kicker box, and you can see where it got its name. The kicking action causes the oils to penetrate the skin. Next, a spinning metal wheel tugs at the pelt to stretch it. The ragged edges are cut away. Then it goes into a hot press. This irons and adds luster to the fur. After a quick brush, the pelts get one more press. Then a shearing machine cuts the hairs to an even length. They bundle up the pelts for a trip to the garment factory, where they'll be great design material. Coming up on How It's Made, welding electrodes. We'll join up with the makers of these clever gadgets. And electric violins. They're loud and they're proud. See you after the break. More than a century ago, welders first fused two metal surfaces by melting a metal stick over them using an electric current. That stick is known as a welding electrode. Farmers and mechanics often use this useful tool to repair heavy machinery. This company's electrodes are coated with powdered metals and minerals. During welding, the metals melt and the minerals protect the area from oxygen, which would weaken the bond. The electrode transmits an electric current that heats and melts both the electrode and the metal surfaces, welding them together. Thin metal wire forms the electrode's core. The type of wire changes dependent on what the electrode's designed to weld. In most cases, the core is made of carbon or stainless steel. A machine simultaneously spins and bends it, reshaping the wire till it's completely straight. 4 metal rollers then push and guide the wire into a guillotine. The blade chops the wire into segments that will become the electrode cores. The factory puts a variety of metals and minerals in the coating. The metals include nickel, manganese and iron. The minerals, alumina, magnesia and limestone. They also add a colorant to identify the different models. Workers mix the ingredients with a little glue until they turn to the consistency of wet sand. A worker then packs the mix into a machine that forms it into slugs with a hole down the middle. He adds a plastic cap. Then a metal cover slides on and the machine takes over. It takes only a minute for the machine's piston to compress the powder into a solid. To put the powder coating on the core wires, a worker loads 4 slugs into an extrusion press. It'll apply 120 tons of pressure to shoot the powder through nozzles that'll coat the wires as they pass through the holes in the slugs. To load them into the press, the wires are first stacked in this feeder. The opening at the bottom can be adjusted because core wires have a range of different diameters. These rollers pass them through the press one at a time. Four wheels then pull the wires from the feeder into the extrusion press for coating at a rate of up to 1,000 electrodes every minute. When the coated electrodes emerge, they hit a metal wheel that positions them on a conveyor. A sander removes up to 5 centimeters of coating from the bottom where you grip the electrode, and it bevels the tip so it conducts electricity even better. A worker now checks for uneven coating and to see if the wire's well centered. The coating dries at room temperature for up to 72 hours. To cure the coating, the electrodes are put in an oven and heated to 485 degrees Celsius for up to 5 hours. Once they've cooled, the electrodes head into a printing press. An ink wheel prints the model and the type of current that's required. Another ink wheel then applies a colour to the gripping end. It's another way to identify the model in case the lettering on the side rubs off in storage. From there, it's off to packaging. An optical scanner counts the electrodes. Then a stacking machine separates them into bundles. Finally, they're inserted into cardboard canisters. A piece of cardboard is added to compress them tightly for the trip. A sticker marks the contents, and tape keeps the package tightly sealed. And to that, we say well done. The invention of the electric violin was all about turning up the volume. In the big band era, the sound of the traditional violin was overpowered by the horns and drums. Amplifying the violin changed everything. Suddenly, the violin wasn't just background sound, it was part of the show. The electric violin comes in different shapes because it doesn't rely on the body to resonate sound. This craftsman builds the violins one piece at a time, starting with the neck. He traces the shape onto a piece of maple. Then he outlines the top plate. Walnut is used for the bottom part, or lower bout, as well as for the backbone of the violin. Next, a bandsaw is used to cut out the shapes. The more precisely the cuts are made, the less sanding will have to be done later. The dimensions for the top and neck are exactly the same as for a traditional violin, so there won't be any difference in the reference points the violinist relies on. The lower bout has a unique design. And the head is more streamlined than a traditional violin. There's no decorative scroll. Next, a cavity is chiseled out of the head of the violin to create the peg box. Parallel grooves are carved into the back to give it a snazzy look. A rasp is used to shave the wood to the correct thickness. Holes for the turning pegs are drilled into the side of the peg box, one for each of the 4 strings. After the grooves on the back have been filed a little more, the rest of the neck is scraped to give it a final finish. The peg holes are tapered using a tool called a reamer. The ebony pegs have matching tapers, so they fit snugly into the holes. Everything is checked to make sure it measures up. Wood glue is brushed onto the neck section, and the ebony fingerboard is pressed onto it. Surgical tubing holds them together while the glue dries. 2 assembly holes are drilled in the top piece, and corresponding holes are made in the other parts. A sander smooths the edges of the backbone. Then, a high-speed router is used to bevel the lower bout piece to give it a clean edge. The wood is stained. The loud colours seem appropriate for these high-volume instruments. A crystal has been glued into the violin's wooden bridge to generate electricity from the string's vibrations and create sound. The wire from the bridge is pulled through the backbone, and then the bout is mounted to the backbone. An ebony chin rest is bolted on top. Next, the neck is attached to the rest of the assembly. The ebony tailpiece is looped on. A string is pulled from the tailpiece to a peg. The act of tightening the first string raises the bridge, which will be held in place simply by tension. Now it's time to hook up the violin to the amplifier and let the music tell the rest of the story. So, whether you're keen to get a look at those holiday snaps, or you want to keep warm, caveman style, or prove what a bright spark you can be with metal, now you know how it's made.